We are in section 3.2. This is part 3, and we will be talking about computer regression output today and how to calculate the least squared regression line using summary statistics and some correlation and regression wisdom. So the first thing we're going to talk about is interpreting computer regression output. And I was going to show you an example. So this figure here displays the basic regression output for the Ford F-150 data from two statistical software packages. One of them is called Minitab and JMP, and then you have other software that also produces similar output. So let's take a look at the Minitab data first. So when you're given the Minitab data on that F-150 truck, S, I mean, that's obvious. There's your standard deviation for your, the S value, which is the standard deviation of the residuals. And then there's R squared, the R squared value, okay, which we've seen those two numbers. And then where it says constant under coefficient, that's your y-intercept, and then this is actually your slope value. So on a Minitab, those are kind of the values that you want to look for that we know that help us right now. We're going to talk about some of these other values later. So then if you look in the JMP file, it does say R squared, so you know that's your R squared value. And then the standard deviation of the residuals is also called the root mean square error. So if you look for that, that's going to be your S value. And then down here again, it'll say the intercept, which that's your y-intercept, and then this is going to be your slope. So I kind of just wanted to show you, you know, these two different kinds of computer output and getting kind of used to what you'll see with those. So the example we're going to do on the note sheet is, first of all, this is foot length and height. So we're going to go through and we're going to do this example and look at the data that they give us. So the problem is a sample of 15 high school students was selected from the U.S. Census at a school database. The foot length and the height of each student sample were recorded. Here's a scatter plot with the least squared regression line added and a residual plot and then some computer output. So let's look up here. We've got the scatter plot with the least squared regression line in here. Here's our residual plot. And then they've also given us this information. And based on what we just discussed here, we know that this is our S value, which is the standard deviation of residuals. This is our R squared value, which is the coefficient of determination. The constant is the y-intercept. And then the foot length here, and it's under coefficient, is your slope. So we could come up with the, you know, we could write the equation for the linear regression line, which would be y hat equals 103.41 plus 2.7469x. There's our R squared, there's our S. Does this data look like linear is the best way to describe it? If you look at this, the scatter plot looks pretty good, going through the middle of most of the points. The residual plot also looks good. There's no curvature. You've got you know, points evenly distributed. So let's answer some questions down here. Is a line an appropriate model to use for this data? Explain how you know. Okay, so really you could use the residual plot. You could also say, hey, this linear regression line goes through the data very nicely, or you could say both things. So what I said was, a line is an appropriate model to use for these data because the scatter plot shows a linear association and the residual has scattered points with no obvious curvature. Because of both of those things, we can say a line is an appropriate model for this data. So let's kind of think about what they're saying here. So The foot length is your explanatory, and your height is your, so the bigger foot length you have, it looks like the taller, obviously, you're going to be. So there is a linear relationship there. Part B, find the correlation. Correlation is our R. And you're like, well, where's the R? Well, we do know what R squared is. So to get the R, you do just take the square root of R squared. And you do want to change that to a decimal instead of a percent. So you're going to take the square root of 0.486. Question C, what is the equation of the least squared regression line that models the relationship between foot length and height? So again, that's what we talked about earlier, that you could come up with the regression equation. So actually these two things were switched. So it would be y hat equals, there's your y-intercept, 103.41 plus 0.27469x. Now it says define any of the variables you use. So what I did is I went underneath and just said that that's your height. Your height prediction is 103.41 plus 2.7469 times x would be your foot length. And then part D, by about how much do the actual heights typically vary from the value predicted by the least squared regression line? That is your S. That is your standard deviation of the residuals that they're asking for. About how much do the actual heights typically vary from the values predicted? That's what S is, okay? So S equals 7.95. So the actual heights typically vary by 7.95 from the values predicted by the regression line. So part D is actually asking you like what S is, and then I kind of went through and content of the problem defined that, okay? All right, so hopefully you don't have any questions on how we came up with that. So this is kind of like our first experience of using just a bunch of data and answering some questions and looking at a mini tab and finding that information that we need. Okay, we're going to do one more example just to make sure you guys are good. So let's read through this. In section 3.1, you read about Old Faithful Geyser in the Yellowstone National Park. The computer output shows the results of a regression of y equals the interval of time until the next eruption, and x is the duration of the most recent eruptions for Old Faithful. So they do give you the mini tab. Well, actually, this is the other, instead of the mini tab, this is the JMP. So this is another way you might see the data. So obviously there's your R squared. There's your S, root mean square. That is your y-intercept here, and then that would be your slope. So where it says intercept, that's your y-intercept, and then the number underneath it would be your slope. So those are the two that you would use. So question 1, what is the equation of the least squared regression line that models the relationship and define any variables that you use? So we would come up with y hat equals, don't forget that's your y-intercept, there's your slope. So y hat equals 33.347 plus 13.285x. X is the duration of most recent eruption, and y is the predicted interval of time until the next eruption. So that kind of was in the problem, and we're just kind of like pointing those out or describing what those things are. Number 2, interpret the slope of the least squared regression line. Okay, so we know that's the slope. What does that mean? Well, basically it means for every minute since the most recent eruption, the predicted interval of time until the next eruption is going to go up by 13.285. So the predicted interval time until the next eruption goes up by 3.285 minutes for each increase of 1 minute in duration of most recent eruption, which is basically what I just said by looking at it. So for every single additional minute until in duration of the most recent eruption, so the predicted interval of time until the next eruption goes up by 13.285 minutes for each increase of 1 minute in the duration of the most recent eruption. So for every additional minute, the wait time is going to go up 13.285. So that's what the slope is. And that's how you always interpret the slope. For every one of these, it's either going to go, this is either going to go up or down if it's a minus this amount for every one of whatever this is. And of course, you have to write it in context. Number 3, identify and interpret the standard deviation of the residuals. Well, that's that S value. So we know that the S value is 6.49 if we round it up. So it means the actual interval of time until the next eruption is typically about 6.49 minutes away from the time predicted by the least squared regression line. And that's always how you interpret the standard deviation, and that you got to do it in context. But basically, you just say, so this is context. The actual interval of time until the next eruption is typically about 6.49 minutes, and then you say away from the time provided or predicted by the least squared regression line. So that's what standard deviation is. It's the average of the residuals, and that's what a residual is. And then the last question is, what percent of the variability in the interval is accounted for by the least squared regression line with x equals duration? So anytime they ask you that word accounted for is your R squared. So, and you want to interpret that as well. So 85.4% of the predicted interval of time until the next eruption is based on duration of most recent eruption. Okay, so 85.4% of the predicted interval of time until the next eruption is based on the duration of most recent eruption. And don't forget to change that to a percentage. They give it to you as a decimal, but usually you see it written as a percentage. So that is using your little data information and how to interpret each. Okay, the next part of the lesson is how to calculate the least squared regression line using summary statistics. We have data on an explanatory variable x. So the explanatory variable we know is x, and the response variable is y for n individuals, and we want to calculate the least squared regression line. From the data, calculate the means, x bar and y bar, and the standard deviation, S sub x and y sub x, of the two variables and the correlation R. And then these two formulas are on the formula sheet I'm going to show you. So here's y hat. It's equal to a plus b x bar. And here's how you find the slope. Okay. So the slope you find, if you look at this, b equals r, which is your correlation, and the standard deviation of the y's divided by the standard deviation of the x's. So you do want to go find that first. So we're going to do an example where we're going to go through, but that formula, and then the way you can find y is by substituting in, and so we'll talk about that with this example. Okay, so this problem says, more about feet and height, calculating the least squared regression line. So they're going to give us some data basically, and you do have the formula so you don't have to memorize them, but you need to go find the least squared regression line. So it says, in the preceding example, we used data from a random sample of 15 high school students to investigate the relationship between foot length in centimeters and height in centimeters. The mean and the standard deviation of the foot lengths are. So the mean of your x's is 24.76, and this is your standard deviation. The mean and the standard deviation of the heights are here, y bar and s sub y. The correlation is 0.697. So you're going to be given all this information. You're going to be asked to find the equation for the least squared regression line for predicting heights from foot length. So the first thing you want to do is you want to go find the slope. So the slope is given here, how to find that. So we have your R, and we have the standard deviation of y and x. So the first thing I did, and it just kind of proves there is a close correlation between slope and R. So I subbed in my R value, which was given over here, 0.697. I subbed in my standard deviation of y, my standard deviation of x. So I got 2.75. Sorry, let me move that back over. So I just went to the formula and I substituted in, and I found my slope to be 2.75. So because the least squared regression line passes through the point x bar, y bar, to find the y-intercept, so this is the formula the book gave, and I think what I do is just sub into this formula. So we knew what y bar was, 171.43. We don't know the y-intercept. So basically, you know, anytime you write an equation, you need to know two things, the slope and the y-intercept. So we found the slope first, and then you do need the slope to help you find what the y-intercept is. So I substituted in y bar, x bar, the slope, and then I solved for a. So there is the equation for the least squared regression line for predicting height from foot length. And again, those formulas are given on the formula sheet. So find the slope first, then you're going to sub that in. You're going to know x bar, y bar, and then that's going to allow you to find the y-intercept. And then once you know those two things, you just write it in the y bar equals a plus bx. So that is how you go through and calculate the least squared regression line using some of those statistics. Okay, so more about correlation. The following four scatter plots show very different relationships. Which one do you think shows the greatest correlation? Which one do you think shows the greatest correlation? Let me get all four of them up here. The greatest correlation. So the greatest correlation would be, correlation is how close it is to a line. So which one do you think would be the answer? I bet most of you guys might pick this one, graph C, okay? Well, let me give you some interesting information. All four have the same correlation, R equals 0.816. All four have the same least squares regression line. Y hat equals 3 plus 0.5x. So when you look at that, I think you're probably a little shocked to see that, okay? These four data sets are referred to as the ASCOM data sets, okay? Correlation measures direction and strength, but not form. So you need to keep that in mind when you talk about R. It's not saying, it's not measuring form, it's just measuring direction and strength. So direction is, you know, that it's positive, and then your strength. So this is just kind of an interesting concept that I think you kind of need to realize about correlation and regression are powerful tools for describing the relationship between two variables. When you use these tools, though, you need to be aware of their limitations, okay? You can calculate the correlation of the least squared regression line for any relationship between two quantitative variables, but the results are useful only if the scatter plot shows a linear pattern. Always plot your data first. So remember, the results are only useful if the scatter plot shows a linear pattern. The following four, the scatter plots that we saw show very different relationships, and I just think it's kind of interesting that, you know, they each both have the same equation there. You already know that correlation is not resistant. One unusual point in a scatter plot can greatly change the value of R. Is the least squares line resistant? The least squared line is resistant. The following activity will help you answer this question. Okay. So the main thing I want you to talk about or learn from this ANSCOM data sets is that you can calculate the correlation of least squared regression line for any relationship between two quantitative variables, but the results are only useful if the scatter plot shows a linear pattern. Okay, what we're going to talk about, the last thing we're going to talk about is the difference between points with high leverage and outliers, okay? Points with high leverage in regression have much larger or much smaller x values than the other points in the data set. An outlier in regression is a point that does not follow the pattern of the data and has a large residual. So if you have an outlier, it's going to have a large residual, and it doesn't follow the pattern of the data. So I think we all kind of know what an outlier is, but I don't know that if you thought about that, it will have a large residual. Whereas points with high leverage have much larger or much smaller x values than the other points on the data set. So we're going to look at some of these in just a second. An influential point in the regression is any point that is removed substantially, if removed, substantially changes the slope, the y-intercept, the correlation, the coefficient of determination, or the standard deviation of the residuals. So let's look at this data over here. Okay, so this is from StatsMedic. This is an outlier, okay? It is far from the other points. This one is an outlier. This is the definition. If you look at it, it would have a very large residual. It doesn't follow the data pattern, and it has a large residual. Okay? This is not an outlier. Like if you look at this point compared to the other data, that would not be an outlier. Okay, so let's look at some different situations. So this scatter plot here really has no unusual points. Okay, if you look at it, the equation is given. The R value is 0.41. The R squared is 0.17 and S is 2.77. So this particular graph, if you look at these points, none of those are unusual. So we're going to look at the different cases. So we've got 4 cases. All right, case 2. So what happened here is you've got the same points you had previously, but now you add this point to it. A point that is far from the other points in the x direction, but the same pattern, okay? So let's compare the difference between the lines are the same. Wow, look at your R and your R squared. Those greatly increased. So what this point did is it kind of, it made the strength of the line a little bit stronger, okay? And this actually, the standard deviation decreased. So the point has a small residual. Because it has a small residual, it changed the standard deviation of the residuals. These two things greatly increased, okay? So this right here would be considered a, this is an influential point. Because if we were to take this out and it went back to this data, these things right here substantially changed, okay? So let's look at case 3. We've got 4 cases. A point that is far from the other points in the x direction and not in the same pattern. So this is not in the same pattern. It is way far away from these x's. This one is way far away from these x's, but it's in the same pattern, okay? So let's look at the equation compared to above. All right, so if you look at the linear regression line, oh my goodness, that is so much different. Look what happened to your R value. It became negative, and the line doesn't fit the points nearly as well. Your standard deviation of the residuals changed a great bit, okay? So we're just kind of looking to see what happens here. All right, a point that is far from the other points in the y direction and not the same pattern. So if we look at this point up here, it does change the line. The residual of new point is much, much larger, okay? So if you look at that standard deviation, goodness gracious, it goes from 2.77 to 10.82. That really changes, and that's because the residual is really changing your standard deviation. All 3 of these unusual points are considered influential points. All 3 are, because adding them to the scatter plot substantially changed either the least squared regression line or one of the either R squared, or S. So this one changed R and R squared greatly. So this is considered an influential point. This one changed the linear regression line so much. That's why this is considered an influential point. And then this one changed your standard deviation. Okay, so all three of those would be considered influential point. Okay, outliers and high influential points, effects on regression. Okay, here we're going to read through this. Does the age at which a child begins to talk predict a later score on the test of mental ability? A study of the development of young children recorded the age and months at which each of 21 children spoke their first word and their Gazelle adaptive score. The result of the aptitude test taken much later. A scatter plot of the data appears along with a residual plot and computer output. 2 points, 18 and 19, are labeled on each plot. So let's take a look at what we have here. So this is their age. This is a scatter plot with the age. And this is how well they, of their first word, their age of their first word. And this is their Gazelle score. So it looks like the later they spoke, it's going in a negative faction. So the later they spoke, the lower their score. And we're going to particularly look at these two children. This is child 18, this is child 19 here. And here is the residual for this data. And so here's the child 19, and here's child 18 here. Okay. So let's answer some questions on this. All right. If you look at this and you, with all possible 19 points, okay, so this red line is without child 19, and this blue line is without child 18, and the green line is with all the points. So this is the line of best fit for all the points. All right, so look what happens if we take out child 18. Look how much that line changes. And then look what happens if we take out child 19. Okay, so if you look at the equations, let's look with all 19, without child 18, without child 19. And then here's your S values. That really changed a lot. And then here's your R squared value. And that really changed a lot. So if you look at these, child 18 has high leverage because the X value is much larger than the other X values. Let's go back and look at the original graph. So child 18, the X values are much larger than these here. So this one does have high leverage, okay? And that's what the definition of a high leverage point is. It has much larger or much smaller X values than other points in the data set. And that's what we saw happen. And then child 19 is considered an outlier because it falls outside the pattern and has a very large residual. So child 19 is actually considered an outlier because it falls outside the pattern and has a very large residual. So if you look back at the data, that's considered an outlier. And child 18 is considered high leverage, okay? So I just kind of wanted to show you the difference between those 3 least squared regression lines of the Gazelle score. The green line is calculated from all the data. Okay, so we already went through all that. All right, last problem. The scatter plot shows the payroll in millions of dollars and the number of wins for Major League Baseball teams in 2016, along with the least squared regression line. The points highlighted in red represent the LA Dodgers, far right, and the Cleveland Indians. So I went through and circled those. So this one here is the Los Angeles Dodgers, and then this one here is the Cleveland Indians. Describe what influence the point represent the LA Dodgers has on the equation of the least squared regression line. Explain your reasoning, and then describe what influence the Cleveland Indians would have. Okay, so talk to me about this. Number one, Do you agree that this X value is much larger than most? Okay. What would happen if we took this point out? Think about the line. If this point goes out, what would happen? Because the point for the LA Dodgers is on the right and below the least squared regression line, it makes the slope closer to 0 and the y-intercept greater. Let me get this on the screen, sorry. So because the point for the LA Dodgers, this one on the right and below the least squared regression line, it makes the slope closer to 0 and the y-intercept greater because it's kind of pulling it down. If the Dodgers point was removed, the line would be steeper. All right, let's talk about this point here. Because the point for the Cleveland Indians has a large residual, it makes the standard deviation greater because the R value, the residual is much greater. So your standard deviation is going to be greater, and it's actually going to make the R squared value smaller. Okay. So that would happen with these 2 points. The term correlation is used only with quantitative variables. That's a reminder. Remember that. That's the term correlation can only be used with quantitative variables. Let's see. I do believe that that is the end of section 3.2. So that wraps up all 3 parts, part 1, part 2, part 3, and hopefully, you know, you have, will be able to complete your homework using these different mini tabs, and then also you're going to have to use these formulas to calculate. You'll usually be given this data, but you could always list this in list 1, list 2, and find those values if you needed to. And then the other important thing is realizing what outliers are versus influential points and the effect that those would have on the least squared regression line and other factors.